also it shows you how quickly these things drop off if you ever wanted to plot the vapor pressure of hydrocarbons with different numbers, right? So adding 2 carbons drops it by 90%, right? 18.828 to 1.82. That's almost a factor of 10 exactly by making that molecule slightly bigger. Well, not slightly bigger. It's actually quite a bit bigger, going from C3 to C5. But you know, the increment gets smaller. But again, it's like this logarithmic behavior. Finally, heptane. No, I didn't give an increment. All right, so they're 0.0227. So it's almost like an order of magnitude, right, for every 2 carbons I have, right? Divide by 10, divide by almost 10, divide by 7. Right? So it's dropping off pretty quickly, the vapor pressure with carbon number. But again, for this point, that's more of a thermodynamics class thing. Anyway, right? But here, we know that our temperature is our temperature, but our pressure assumption was fine. And if we didn't know that, I mean, what we could have done then was just got all the vapor pressures at 55 C anyway, and then figured out our working range and picked one that would work in that range, right? 3.2 atmospheres, we'll stick with that. Okay, so next then, let's do xi. Okay, so obviously xi is one thing we're going to need to solve for. We can put L xi, right? So the total molar flow rate. Likewise, we need yi. And VYI. All right, so LXI and VYI, right, we can reference those. And for now, let's just plug in 0.25 because these are going to change, right? So if they're all the same, then nothing's happening. But for now, I'm just plugging those in as a guess, so those cells aren't empty, right? So then we can say sum, better than that. So let's just do the sum of these, right, as kind of a check. Sum these. I'm going to make that black. So we realize it's not something we should be trying to change, or that's not going to be affected by the calculations. And then I can also do a K, right? So if I want to, I can actually calculate the K values from this as well, right? Because K is just Y over X. Right, so right now they're all K's of 1, but that's going to change, obviously, right? So what we need to do then is also get a total pressure, right? So Xi is really what we're solving for. I plug that in, but Yi is not just Yi, right? Yi, going back to this, right? So Yi is Xi P star I divided by P. Right? So Yi is not independent. I plug that in, but it's not accurate, right? So this is equal to that, Xi times P star I divided by our total pressure. Let's make that a static reference. Right, so if I just did that, I don't get an answer, right? I mean, I get an answer. It's not the answer I want, right? Because 1.634 is wrong, right? So we need to fix that, right? And we can have a check too, right? So xi, p star I, right, we could actually put that as a cell. All right, so we can calculate whether or not the pressures are adding up. I like the way that looks better than this. That's good. All right, so if I want to check these things, right, then I can say this is equal to this cell times this cell. So the total pressure, right, Yi, well, the partial pressure, right, so again, we don't usually write it like this, but I know I wrote this maybe early on. Pi, right, so that's the partial pressure, is also equal to xi. P star I, T, right, so the sum Pi